leaving the icy mysteries of comets behind. We now journey to one of the most mesmerizing and enigmatic planets in our solar system, Saturn. Known for its dazzling rings and countless moons, Saturn holds secrets that could reshape our understanding of planetary science and the possibilities of life beyond Earth. Let's uncover them. Cassini. Unlocking Saturn's Secrets. On October 15, 1997, the Cassini-Huygens spacecraft embarked on an extraordinary journey to Saturn, launching aboard an 1,100-ton Titan IVB rocket from Cape Canaveral. This was no ordinary mission. Saturn, lying nearly 900 million miles away, had not been visited by a spacecraft in over 25 years. The planet, with its iconic rings and over 60 moons, is a massive gas giant, more than 750 times the mass of Earth, and lacks a solid surface. The last mission to Saturn, conducted by the Voyager spacecraft, revealed tantalizing glimpses of this distant world. Images showed thick, banded clouds swirling in the planet's atmosphere, and infrared cameras detected signs of storm activity beneath the haze. But Voyager's mission was limited. It was a flyby, capturing only fleeting snapshots as it sped past at thousands of miles per hour. Scientists were left with far more questions than answers. Voyager 1's brief encounter with Saturn's largest moon, Titan, was especially intriguing. Its instruments detected organic compounds in Titan's atmosphere, compounds similar to those that formed the building blocks of life on Earth 4 billion years ago. Scientists saw Titan as a time capsule, offering a glimpse into the chemical processes that may have led to life on our own planet. Yet, like with Saturn itself, Voyager 1 had no opportunity to linger. At a velocity of 39,000 miles per hour, it hurtled away into the outer solar system, leaving behind a trail of unanswered questions. The discoveries made by Voyager inspired a new mission, one that could delve deeper into Saturn's mysteries and those of its enigmatic moon, Titan. We want to understand our own origins, scientists explained. Why did Earth become what it is? How did life emerge here? By studying Saturn and its moons, they hope to unlock answers to these profound questions. Cassini was a technological marvel, one of the most advanced spacecraft ever built. Equipped with an array of high-tech cameras and sensors, it was designed to study Saturn's atmosphere, rings, and moons in unprecedented detail. Alongside it traveled Huygens, a small probe destined to explore Titan. The probe was engineered to descend through Titan's dense atmosphere and land on its surface, making history as the first human-made object to do so. Reaching Saturn, however, was no small feat. The mission required navigating a 2 billion-mile journey through the solar system. To conserve fuel, Mission Control used the gravitational pull of nearby planets as a slingshot, propelling the spacecraft through a series of flybys around Venus, Earth, and Jupiter. This clever use of gravity gave Cassini the momentum it needed to reach its distant destination. After 7 years of travel, Saturn finally loomed into view. The spacecraft began sending back images of the gas giant, each one more stunning than the last. Saturn's ethereal rings, composed of billions of ice particles, shimmered against the darkness of space. But before Cassini could begin its detailed exploration, it faced a harrowing challenge. It had to pass through the rings themselves. The rings of Saturn, while breathtaking, are also perilous. Stretching over 170,000 miles, they are composed of particles ranging in size from tiny grains of dust to chunks as large as a house. Any collision with these particles could prove catastrophic for the spacecraft. Cassini's team meticulously calculated its trajectory, navigating through a gap in the rings where the risk of collision was minimal. As Cassini threaded its way through this celestial obstacle course, its instruments captured the most detailed images of Saturn's rings ever seen. The spacecraft revealed the complexity of their structure: dense bands interspersed with gaps and delicate wave-like patterns caused by the gravitational pull of Saturn's moons. With this successful maneuver, Cassini had overcome its first major hurdle. Now, the spacecraft was ready to begin its historic exploration of Saturn. A mission that would last 13 years, transforming our understanding of this majestic planet and its mysterious moons. Cassini's journey was just beginning, and the secrets it would uncover would astonish scientists and reshape our knowledge of the solar system. Saturn's rings, while breathtakingly beautiful, are a chaotic and perilous maze. Made up of billions of particles of ice and rock whizzing around the planet at high speed, they include fragments as large as houses. For Cassini to reach its destination, it had to navigate a narrow gap between the rings, a maneuver fraught with risk. As Cassini approached, the tension at mission control was palpable. Dr. Jeff Kuzi, overseeing the spacecraft's entry, described the gap as something you wouldn't see with your eye, emphasizing the precision needed for the task. It was like threading a needle across 900 million miles of space. Cassini fired its rocket engines to align its trajectory and aimed for the gap. To shield itself from potential damage, the spacecraft turned its antenna away from Earth, cutting off communication during this critical phase. All the team could do was wait. Dr. Larry Esposito, part of the mission team, described the anticipation as excruciating. Everyone was holding their breath, waiting for the signal to come from the spacecraft. Hours passed before Cassini's signal finally returned. It had successfully navigated the ring plane. Relief swept through mission control, giving way to cheers, handshakes, and even tears. After decades of planning and 7 years of travel, Cassini had become the first spacecraft to enter orbit around a planet in the outer solar system. With Cassini safely in orbit, the mission's true work could begin. For the first time, a spacecraft had the opportunity to observe Saturn up close for years, capturing data from multiple perspectives. Dr. Tony Del Genio celebrated this historic milestone. The beauty of the Cassini mission is that, for the first time, we get to go into orbit around a planet like Saturn, and, for years, observe it over and over again from different angles. Finally, some of the secrets start to be revealed to us. Cassini's first task was to explore Saturn's thick atmosphere. Maneuvering toward the South Pole, it made a startling discovery: a massive hurricane-like vortex, unlike anything ever observed outside Earth. This monstrous storm, more than 1,000 miles wide, dwarfs hurricanes on Earth. Its eye is encircled by a towering wall of clouds, rising an astonishing 45 miles high, while winds roar at 350 miles per hour. Temperatures in the upper layers of the storm plummet to -167 degrees Fahrenheit, creating flurries of ice crystals that Cassini's cameras captured in stunning detail. The storm's scale and behavior mirrored hurricanes on Earth, with swirling clouds and a defined eye. But its size and power were uniquely Saturnian, a testament to the extremes of this gas giant. Cassini's journey through Saturn's orbit was just beginning, but even in these early moments, it had already transformed humanity's understanding of this distant world. For the first time, Saturn was not just a shimmering light in the sky, but a dynamic, complex planet with secrets waiting to be unraveled. Decoding Saturn's storms. The power within Saturn's immense swirling storms have captivated scientists. Like Earth's hurricanes, they feature swirling clouds, powerful winds, and even snow. It definitely snows on Saturn, one scientist noted. In the upper reaches of these storms, large ice crystals form and fall, while deeper within, hidden from view, liquid water rain likely pours out of the storm clouds. But what powers these colossal tempests? Unlike Earth, where hurricanes are fueled by the sun's energy and warm ocean waters, Saturn is far too distant from the sun to draw enough energy for its massive storms. The mystery lies deeper within the planet itself. Saturn, a gas giant, has no solid surface to slow its winds. Once a storm starts, it can persist for long periods, circulating energy across the atmosphere. Still, without a continuous energy source, even these winds would eventually dissipate. Many scientists believe that the energy fueling Saturn's storms comes from deep inside the planet. Driven by heat left over from Saturn's formation and the gravitational compression of its massive layers. Cassini captured mesmerizing images of Saturn's most powerful storms, including a hurricane-like vortex at the planet's south pole, where winds roared at over 350 miles per hour. The storm's sheer scale, a swirling tempest 2/3 the size of Earth, left scientists in awe. But while its intensity was clear, its energy source remained elusive. In the Coriolis laboratory in France, astrophysicist Peter Reed set out to test the theory that internal heat drives Saturn's storms. Using an innovative experiment, Reed sought to recreate the turbulent atmosphere of the gas giant in a controlled environment. At the heart of the experiment was a giant rotating tank containing nearly 40,000 gallons of fluid. The fluid acted like Saturn's gaseous atmosphere, while a heater at the base of the tank simulated the internal heat radiating from the planet's core. To mimic the behavior of Saturn's clouds, light-sensitive particles were suspended in the fluid. These particles, carried by the artificial winds, allowed scientists to visualize the currents and vortices forming in the tank. The tank was set spinning to emulate Saturn's rotation. As the fluid moved, the tiny particles began to interact, creating swirling patterns reminiscent of Saturn's jet streams and storm bands. Slowly but surely, the particles organized into eastward and westward jet streams, with distinct vortices forming, just like the stormy bands observed on Saturn's surface. The experiment demonstrated that internal heat combined with the planet's rapid rotation could organize atmospheric patterns into the banded structures and powerful jet streams seen on Saturn. "We can see evidence of a jet structure," Reed remarked, pointing to the fluid in motion. "And here we can see a very nice rotating structure." While the experiment didn't provide all the answers, it offered strong support for the theory that heat from Saturn's interior drives its colossal storms. These findings bring scientists closer to understanding the mechanics of gas giant atmospheres, not just on Saturn, but on other planets like Jupiter and Neptune as well. As Cassini continued its mission, the insights from experiments like these gave researchers new tools to interpret the spacecraft's findings, unraveling more of Saturn's secrets and reshaping humanity's understanding of planetary science. The hidden power of Saturn's core. Saturn's anticyclonic vortices, with their swirling patterns of clouds, continue to amaze scientists. Experiments like Peter Reed's have hinted that a heat source deep within the planet fuels its monstrous storms. But what exactly lies at Saturn's core to generate such immense energy? Saturn, composed of approximately 75% hydrogen and 25% helium, with traces of methane, water, and ammonia, is a gaseous world. Yet, scientists believe it hides a hot, rocky core, roughly the size of Earth, surrounded by extreme pressure zones that hold the key to its energy. On Earth, internal heat comes from the radioactive decay of materials in the core and residual heat from its formation. But in Saturn, heat generation operates on a different scale. Near its core, the pressure is so immense, millions of times greater than on Earth's surface, that hydrogen and helium gases are compressed into metallic liquids. If you get deep enough, one researcher explains, the hydrogen and helium become so dense that they don't behave like gases anymore. They act like electrically conducting metals. These liquids swirl around Saturn's rocky core, but they do not mix. The heavier helium sinks through the hydrogen, creating friction and releasing heat in the process. This mechanism may explain why Saturn emits 3 times more heat into space than it receives from the Sun. To investigate further, Cassini has been collecting precise measurements of helium levels in Saturn's atmosphere, providing vital clues to this dynamic process. The data is so extensive that it will take years to analyze, but scientists are optimistic about uncovering the secrets of Saturn's internal energy. Cassini's mission now shifts outward to examine one of Saturn's most iconic features: its spectacular rings. These rings, first revealed in detail by the Voyager missions over 25 years ago, remain the largest and most dynamic in the solar system. Composed of billions of chunks of ice and rock, Saturn's rings resemble a turbulent boulder field, with particles ranging in size from mere fractions of an inch to several yards across. The constant collisions between these fragments create an ever-shifting landscape of chaos and beauty. If you were to fly over the rings very close, you'd see something that looks like a flying boulder field, a scientist remarked. The ring's turbulent activity sparked an intriguing question. Could the processes shaping them mirror the formation of planets in the early solar system? Over 4.5 billion years ago, a similar disk of gas and dust encircled the young sun. As particles clumped together over millions of years, they grew larger, eventually forming the planets we see today. Cassini's high-resolution images of Saturn's rings offer a stunning glimpse into this analogy. The detailed snapshots show particles aggregating, hinting at the same mechanisms that might have operated in the protoplanetary disk of the solar system's infancy. I was very, very excited to see these beautiful, beautiful images, one mission scientist shared, reflecting the awe Cassini inspires. By studying Saturn's rings, scientists gain a unique window into the processes that shaped our solar system billions of years ago. Cassini's findings suggest that the same forces acting within the rings today may have sculpted the planets in the distant past. As the spacecraft continues its journey, its discoveries are not only redefining our understanding of Saturn, but also offering a glimpse into the cosmic forces that shaped the very world we call home. Cassini's revelations, Saturn's rings, and the mystery of Titan. Cassini's exploration of Saturn's rings provided scientists with some of the most detailed images ever captured, transforming their understanding of these celestial structures. Using an ultraviolet imaging spectrograph, Cassini mapped the intricate structure of the rings with astonishing clarity. The spectacular detail we saw was an eye-opener, one scientist remarked. As particles in the rings passed in front of distant stars, the UV spectrograph measured the amount of starlight that filtered through. Areas with dense particle concentrations blocked the starlight, appearing darker, while less dense regions allowed more light to shine through. The darker regions revealed fascinating structures called moonlets, temporary clumps of particles that appeared as bright lumps in Cassini's images. Scientists believe these moonlets are aggregations of smaller particles, held together by gravity and surface stickiness. These big boulders may be nothing but an agglomeration of smaller ones, a researcher explained. As they bump into each other, they may collapse and fall apart, only to reform over time. This discovery fascinated scientists, as it echoed the processes that shaped the early solar system. Over billions of years, microscopic specks of dust interacted and clumped together to form the planets. The interaction between the moonlets and the ring particles is exactly like the interactions between a planet and the dust collecting to make that planet grow, one researcher observed. Cassini's images offered unparalleled insight into the mechanisms of planetary formation, providing a glimpse into how our solar system and our world came to be. Despite their grandeur, the origin of Saturn's rings remained a mystery. Scientists hypothesized that they formed during the solar system's violent early years, when comets and asteroids frequently collided with young planets, creating explosive impacts and leaving scars that endure to this day. Saturn's moon Mimas illustrates the destructive power of these collisions. A massive crater dents its surface, a scar from a catastrophic impact that the moon narrowly survived. But other moons may not have been so lucky. Scientists believe that one of Saturn's ancient moons could have been shattered during a collision, breaking apart into billions of fragments. Saturn's immense gravity likely captured these fragments, compressing them over time into the flat, luminous plane of icy particles that now encircle the planet. These rings, born from destruction, offer a window into the solar system's turbulent infancy. As Cassini completed its study of Saturn's rings, its next target was Titan, Saturn's largest moon and one of the most enigmatic worlds in the solar system. Titan is massive, weighing nearly twice as much as Earth's moon, and its thick orange atmosphere has puzzled scientists for decades. In 1980, Voyager 1 sent back the first images of Titan. Shrouded in haze, the moon's surface was hidden beneath its dense atmosphere. The presence of organic compounds suggested that Titan's environment might mirror that of early Earth, offering scientists a unique opportunity to study processes that could have led to the development of life. To explore this mysterious moon, Cassini carried a secondary probe called Huygens, designed specifically to land on Titan's surface. With this mission, scientists hope to peer beneath the haze and uncover the secrets of a world frozen in time. A glimpse into Earth's past before life began. Having crossed over 2 billion miles of space, Cassini and Huygens were poised to deliver groundbreaking discoveries, unlocking not just the mysteries of Titan, but also clues to the evolution of planets and the origins of life itself. As the spacecraft approached this intriguing moon, anticipation reached a fever pitch. Titan, a world unlike any other, awaited exploration. Titan, a world like no other Titan, Saturn's largest moon, holds an atmosphere strikingly similar to that of early Earth. Composed primarily of nitrogen, it also contains water vapor and traces of organic compounds like ethane and carbon dioxide, key ingredients that could potentially serve as the raw materials for life. For scientists, Titan offers a glimpse into Earth's distant past, making it one of the most intriguing destinations in the solar system. The Huygens probe, carried by Cassini, was tasked with solving the mystery of what lies beneath Titan's thick orange haze. Dr. Carolyn Porco, who had worked on the Voyager mission decades earlier, expressed the immense anticipation among scientists as Cassini returned to the Saturn system. You can imagine the excitement of coming back to study a place that had captivated us 24 years earlier. Cassini's cameras alone couldn't fully penetrate Titan's dense atmosphere, leaving its surface obscured and enigmatic. Early images painted a mystifying picture, hinting at an alien world but revealing little detail. To uncover the secrets beneath the haze, the Huygens probe plunged into Titan's atmosphere at over 13,000 miles per hour. At first, Huygens cameras transmitted only images of thick yellow haze, making the descent seem like a journey into the unknown. But at around 30 miles above the surface, the haze began to clear, and Titan's landscape came into focus. The first images revealed a desert-like terrain of low hills and rolling plains, an alien world unlike anything seen before. Dr. Ralph Lorenz, a mission engineer, shared the team's anxiety about where Huygens would land. "We didn't know if it would survive. It could have landed in a lake of liquid hydrocarbons, on ice, or even a sand dune." To everyone's relief, Huygens touched down on level ground and survived. It became the first probe to land on another world in the outer solar system. Huygens's onboard cameras and instruments revealed an eerie alien landscape. A penetrometer, designed to measure the texture of the surface, detected ground with the consistency of damp sand or soft clay, possibly with a crust on top. Lorenz joked, "It was like crème brûlée." The most astonishing discovery came from the camera's images, which showed smooth, rounded pebbles scattered across the surface. These pebbles resembled those found in Earth's riverbeds, suggesting that they had been tumbled in flowing liquid. The surrounding area, marked by river gullies, indicated that rain had once fallen on Titan, carving channels and washing down these rocks. Huygens's findings provided the first unambiguous signs of liquid activity on Titan's surface. A groundbreaking revelation. The discovery of a riverbed posed another question. What liquid could have carved it? Huygens's instruments measured Titan's surface temperature at a frigid 290 degrees Fahrenheit below zero, far too cold for liquid water. At such temperatures, water would be as solid as rock. The answer lay in Titan's unique climate. Instead of water, liquid methane and ethane, hydrocarbons that remain liquid in Titan's bitter cold, likely flowed across its surface, carving the riverbed and creating the smooth pebbles observed by Huygens. As Huygens continued to probe from the ground, Cassini shifted its focus, to Titan's uncharted North Pole. Using radar to penetrate the dense smog, Cassini uncovered a startling discovery. Dark patches scattered across the region. These patches, invisible in optical wavelengths, suggested something astonishing: large bodies of liquid. Titan's North Pole appeared to host seas and lakes of liquid methane and ethane, providing further evidence of a dynamic, alien world shaped by flowing hydrocarbons. Huygens and Cassini together unveiled a Titan that is both eerily familiar and profoundly alien. With an atmosphere resembling early Earth and evidence of liquid activity on its surface, Titan offers a unique laboratory to study processes that could one day lead to life. As Cassini continued its exploration, Titan's secrets began to unfold, shedding light not just on this mysterious moon, but on the origins of Earth and the potential for life elsewhere in the universe. Titan remains a testament to the power of exploration and humanity's relentless quest to understand our place in the cosmos. Titan, Saturn's largest moon, continues to astonish scientists with its alien yet familiar features. Its surface, shaped not by water but by liquid methane, offers a fascinating glimpse into an otherworldly hydrological cycle. While temperatures on Titan plunge far below freezing, making water as solid as rock, methane remains liquid, flowing across the surface and carving riverbeds, gullies, and lakes. Cassini's visual and infrared mapping spectrometer captured dramatic images of a massive cloud system engulfing Titan's North Pole. These clouds, composed of methane, appear to supply the liquid filling the moon's lakes. "We've counted up the volume of liquid in some of these lakes," a scientist noted, "and it's hundreds of times the amount of all the liquefied natural gas and oil on Earth." This methane-based hydrological system operates similarly to Earth's water cycle, with evaporation, cloud formation, and precipitation. But Titan's surface conditions, with frigid temperatures and frozen water, are inhospitable to life as we know it. If Titan's surface seems unwelcoming, its atmosphere tells a different story. Scientists are captivated by the tiny particles suspended in its nitrogen-rich skies, first discovered decades ago by Voyager. These particles are a cocktail of organic molecules, the same kind of substances that existed on Earth 4 billion years ago, when life was beginning to take shape. Understanding how these molecules form on Titan could unlock the secrets of how life developed on Earth. Cassini's instruments isolated the exact mix of these molecules and transmitted the data back to mission control. Astrobiologist Dr. Chris McKay, who had spent years simulating Titan's atmosphere in the lab, was thrilled by the findings. "As soon as the Cassini results came in, we scrambled to adjust our experiments," McKay explained. "It was like seeing the answer at the back of the book after working on a problem for a decade." McKay recreated Titan's environment in his lab, simulating its pressure, temperature, and methane-rich atmosphere. A mixture of methane and nitrogen was passed through a reaction chamber, where an electric discharge simulated the sun's ultraviolet radiation. "This is Titan in a jar," McKay said, as the experiment replicated Titan's atmospheric processes. Within hours, simple molecules like methane and nitrogen transformed into complex nitrogen-rich compounds called tholins. These substances, which Cassini had detected on Titan, resemble the precursors of life's building blocks on Earth. The tholins produced in McKay's lab were nearly identical to those found on Titan, offering a unique opportunity to study the chemistry that might lead to life. One of the big questions is whether the chemistry that led to life on Earth is a rare, unique process or a common occurrence on planets like Earth, or even moons like Titan, McKay remarked. If Titan's processes mirror those of early Earth, it suggests that life might not be unique to our planet. Instead, the steps that lead to life, organic chemistry, energy input, and the right environmental conditions might be commonplace in the universe. Cassini's exploration of Titan shows how life could emerge on other worlds, offering hope for discovering life beyond Earth. After more than 3 hours of groundbreaking data collection and 750 stunning images, Huygens' batteries finally died out. Its landing on Titan marked one of the most significant achievements in the history of space exploration. The probe provided humanity with its first close-up look at a moon that could hold clues to the origins of life itself. As Huygens' mission concluded, Cassini continued its journey, leaving Titan behind to explore another of Saturn's enigmatic moons, Enceladus. This icy world, with its hidden subsurface ocean, promised even greater revelations about the potential for life in our solar system. With every discovery, Cassini reaffirmed the importance of exploration, revealing the extraordinary possibilities that lie beyond our home planet. The surprising secrets of Enceladus. As Cassini continues its exploration of Saturn's moons, it turns its attention to the icy and enigmatic Enceladus, one of the brightest objects in the solar system. Cassini's cameras capture breathtaking images of this frozen moon, revealing a surface marked by fractured plains, craters, and folded mountains. Enceladus is a dazzling world, but beneath its icy exterior lies an even greater mystery. During a close flyby, Cassini's magnetometer detects a peculiar disturbance in Saturn's immense magnetic field. The moon appears to be emitting gas, suggesting the presence of a tenuous atmosphere. This discovery is unexpected. Enceladus is just 300 miles across, far too small and with insufficient gravity to retain an atmosphere for long. Initially, planetary scientists, including Professor Bob Brown, were skeptical. "An object like this can't have an atmosphere," Brown remarked. But as the data continued to flow in, the mystery deepened. Cassini's instruments revealed that the atmosphere-like phenomenon was concentrated around Enceladus's south pole. Such a localized atmosphere defied conventional understanding. Atmospheres should be distributed uniformly around a celestial body. Determined to uncover the source of this anomaly, Cassini moved closer to Enceladus. What it found was astonishing. Giant geysers at the South Pole erupting into space, launching massive plumes of vapor over 400 miles high. The sight of the jets left scientists in awe. It was one of those discoveries that happens once in a lifetime, a team member recalled. Using its spectrograph, Cassini analyzed the composition of the vapor. The results were mind-blowing. The plumes contained water. The implications were profound. Could liquid water, a critical ingredient for life, exist beneath the icy crust of this tiny moon? Cassini zeroed in on the cracked terrain at Enceladus's south pole, an area that appeared to hold the key to the geysers. These regions were far warmer than expected, with temperatures potentially reaching 0 degrees Celsius, warm enough to allow liquid water to exist just below the surface. This discovery was as puzzling as it was exciting. It's one thing to find a warm body, a scientist explained. But it's entirely different to find that it's warm only in one location. The heat appeared to be confined to the cracks, suggesting an internal heat source driving the activity. Enceladus, once thought to be a frozen and inert world, now seemed alive with dynamic processes. The localized warmth and water-rich plumes hinted at the possibility of a subsurface ocean, raising questions about the Moon's potential to support life. For Cassini, this discovery marked the beginning of a new chapter, transforming Enceladus from a small, icy satellite into one of the most exciting destinations in the solar system. Enceladus, a world of possibilities. The discovery of localized warmth and water-rich plumes on Enceladus has left scientists scrambling to understand what generates these pockets of heat. One prevailing theory centers on the Moon's elliptical orbit around Saturn. As Enceladus moves closer to the planet, tidal forces flex its icy crust, creating friction at fault lines. When it moves farther away, the crust relaxes. This continuous flexing generates heat, possibly enough to melt the ice within the faults. Enceladus flexes its body, and that can produce friction enough to melt ice, to create liquid water, one researcher explained. The prospect of liquid water on this frozen moon demands further exploration. To uncover the secrets of Enceladus's plumes, NASA directed Cassini to fly just 30 miles above the Moon's surface, passing directly through the jets of vapor erupting from the South Pole. The spacecraft's instruments analyzed the plume's composition, and the results were astonishing. The plumes contained water vapor, nitrogen, and simple organic molecules. These ingredients, water, heat, and organic chemistry, are the fundamental components needed to support life. It doesn't take much of a jump at that point to make the association, a scientist remarked. If you have water, heat, and organic chemicals, you have the conditions that might actually produce primitive life. The evidence suggests that beneath Enceladus's icy crust lies a subterranean sea, possibly connected to the surface through deep faults. This dark, sunless world could still harbor life. On Earth, similar environments exist at hydrothermal vents on the ocean floor. These vents, which spew hot, mineral-rich water, support thriving ecosystems of primitive organisms despite the extreme conditions. There's the possibility of having something akin to those hydrothermal vents that we see at the bottom of the ocean, a scientist noted. And we know there are living organisms there. If life exists on Enceladus, even in its simplest forms, the implications would be profound. What could be a more important scientific discovery than to find out life has evolved separately in some other place? A researcher asked. That changes the whole picture for human beings. If scientists can confirm that life originated independently on Enceladus, it would suggest that the processes leading to life are not unique to Earth. Such a discovery would break the notion of Earth's exclusivity, implying that life could be common throughout the cosmos. On April 15, 2018, NASA extended Cassini's mission for another 2 years, dedicating part of this time to further explore Enceladus and Titan. As Cassini continues to probe these moons, the possibility of finding life looms larger than ever. Enceladus offers a tantalizing glimpse into the potential for life beyond Earth. But it also underscores how fragile life is in the hostile environments of the solar system. On Earth, life thrives thanks to the magnetosphere, an invisible shield protecting the planet from cosmic radiation. However, new evidence suggests this shield is weakening, with dangerous radiation levels emerging above the South Atlantic. It's not a matter of if the Earth's magnetic field will disappear someday, it's a matter of when, one scientist cautioned. The search for life on Enceladus reminds us not only of the possibilities beyond our planet, but also of the delicate balance that sustains life on Earth. As we explore the cosmos, we may learn how to protect our home, and perhaps one day, find another. Thank you for watching.